30 years have been witness to a series of the most rapid and revolutionary changes of any time in modern history. Of these changes, two which occurred in 1945 have been of enormous significance. The beginning of the atomic age and the founding of the United Nations. While the timing of these events may have been coincidental, the link between them has been intrinsic and continuous. From its beginning, the UN has been committed to the idea that the power of the atom should be controlled and channeled away from weaponry toward peaceful and constructive uses. Their efforts in this direction took a major step forward when, in 1954, President Dwight D. Eisenhower proposed the establishment of an International Atomic Energy Agency. The new organization, the IAEA, was to assist in and assure the development of atomic energy for the benefit of all mankind. 3 years later, in 1957, the IAEA statute came into force. Headquarters for the agency were located in Vienna, Austria. In 1979, the IAEA moved to its permanent location in the Vienna International Center. From here, the agency administers and directs worldwide programs of research and technical assistance to make the benefits of nuclear technology available to its member states throughout the world. A major activity of the IAEA is the implementation of a nuclear safeguards program. It ensures that nuclear materials and technology intended for peaceful applications are not diverted to weapons use. In nuclear power plants, for example, fissionable materials in various forms and quantities pass through the nuclear fuel cycle. IAEA safeguards procedures are designed to monitor these materials in order to detect any attempts to divert them to unauthorized uses. The fundamental safeguards measure used by the agency is a system of material accountancy. In safeguarded facilities, material balance areas are established, which encompass those portions of the plant involved with the processing, use, or storage of nuclear materials. The flow of nuclear fuels into or out of these areas is closely monitored and accounted for under an accounting system established by the state in which the facility is located. The accounting is independently verified by the International Atomic Energy Agency during periodic on-site inspections by agency personnel. The inspectors, mutually designated by the IAEA and the member state, examine the records and make independent measurements to assure that all safeguarded materials are accounted for. Secondary safeguards measures used to complement material accounting are called containment and surveillance. Used together, containment and surveillance can substantially increase the efficiency and effectiveness of the inspection process. These measures use strategically placed surveillance devices to monitor containment vessels, storage areas, or equipment used for material transport. Thus, the movement of nuclear materials can be detected and recorded between inspector visits. The information obtained is used by the agency to preserve the integrity of prior accounting measurements and to thereby reduce the frequency of taking material inventories for verification purposes. Currently, 3 types of surveillance devices are used by the agency in the nuclear safeguards program. Seals, both metal and electronic, which indicate whether or not a containment has been breached. Time-lapse film cameras, which record the events at containment areas. And videotape camera systems for recording events in high radiation environments or over long periods of time. The IAEA is conducting a series of R&D efforts aimed at further development of safeguards technology. These programs are supplemented by technical assistance efforts provided by some of the agency's member states. The United States, for example, has initiated several programs in cooperation with the agency to provide further technological improvements in the area of safeguards implementation. These initiatives are geared toward applying unique U.S. technology to enhance the cost-effectiveness of the agency's safeguard program. Through the U.S. program, the Departments of Energy and State, the Nuclear Regulatory Commission, and the U.S. Arms Control and Disarmament Agency combine their expertise and resources in the form of R&D projects, technical experts, and other support as needed and requested by the IAEA. In addition, each of the agencies supporting the overall U.S. program has on its own initiated projects in support of international nuclear safeguards. For example, ACDA, the Arms Control and Disarmament Agency.
Through its nuclear safeguard staff, the United States Arms Control and Disarmament Agency is sponsoring a range of research projects which we hope will assist in the effective and efficient application of IAEA safeguards. Our research program touches on all areas of international safeguards and includes both studies and equipment development. In order to put this program into its proper perspective, and in particular, one of our major projects in the area of containment surveillance, let me take a moment and go back to the basic IAEA safeguards objective. And let me quote, "The timely detection of diversion of significant quantities of nuclear material from peaceful nuclear activities to the manufacture of nuclear weapons or other nuclear explosive devices or for purposes unknown, and the deterrence of such diversion by the risk of early detection." The significant quantities referred to here relate to the approximate amount of nuclear material required for the manufacture of such a device. On the other hand, the timeliness of detection relates to the approximate amount of time required to convert such materials to nuclear explosive use. This factor of timeliness of detection, ranging from the order of weeks to up to a year, is intended to provide sufficient time for appropriate international diplomatic action before an explosive device may have been manufactured. And most important of all, a credible safeguard system is designed to serve as a deterrent for such diversion and thus to enhance international stability.
Meeting the timeliness criterion will become increasingly difficult as a greater number of increasingly complex nuclear facilities come under IAEA safeguards. One of ACDA's major research projects addresses this future requirement. It's called the RECOVER program. The purpose of RECOVER is to provide the agency the capability to continually monitor from its Vienna headquarters safeguards devices deployed at nuclear facilities worldwide. When implemented for IAEA use, RECOVER will provide a continuity of knowledge regarding the status of safeguards equipment during the intervals between inspector visits. At a nuclear facility where RECOVER is installed, each safeguard sensor which interfaces with the system contains a RECOVER monitoring unit, or MU. The monitor gathers at fraction of a second intervals status data, integrity assurance, and performance indicators from the sensor. This information is retained in the monitor's file. At programmed intervals, each monitor is interrogated by another RECOVER component at the monitored facility, the on-site multiplexer. When properly addressed, Each monitor encrypts the status data in its file for transmission to the single multiplexer at that facility. Notice that the communications between the monitors and the multiplexer can be conducted by either hardwired lines, RF transceivers, or by power overlay systems. The multiplexer retains both historical and continuously updated status data on all its monitors until it's interrogated by IAEA headquarters. If the query is properly made, the data in the multiplexer's file is encrypted for transmission to Vienna. Communications between the multiplexer and the Vienna command console is via the worldwide dial-up telephone network. A modem is used to connect the multiplexer to the local telephone lines, which in turn connect to the international network. The resident verification unit in Vienna receives all incoming data from the multiplexers and displays it as CRT images or as printed lists. Status changes are noted and recorded. Certain status changes which are considered to be of particular interest are displayed as alerting conditions and require acknowledgement by an authorized person at the agency. A fourth recover component is the portable verification unit. It's used by the IAEA inspector to install monitors and multiplexers on site. It also loads the encryption keys in the on-site components. If connected to a multiplexer, the portable verifier can decode and display all transmissions to the central console in Vienna. It's also used as a diagnostic tool for locating malfunctions in the recover system.
Design specifications for the recover system were based on criteria which would assure a system that is operationally simple, reliable, cost-effective, secure, and practical for use by IAEA in nuclear facilities. To a great extent, the recover system design utilizes off-the-shelf industrial-grade components. The microprocessors used in the monitor, multiplexer, and portable verification units, for example, are standard devices used in the automotive industry and produced at a rate of more than 12 million per year. System functions were allocated among the recover hardware units so that those requiring highest volume production, the monitors, are the simplest and least expensive. In the software, processing and encryption algorithms used at the lower levels are also used in higher level devices to reduce the design cost and to facilitate future system expansion.
The recover system is being developed and built under contract to ACDA by TRW. TRW is an international corporation with a history of leadership and expertise in microelectronics, data communication, and distributed data processing. The TRW Recover team is based in Washington, D.C. An experienced staff of administrative and engineering personnel manages the global support effort TRW provides to the Recover program. This includes designing the interfaces to existing IAEA sensors, design and building of Recover hardware and software subsystems, and assessment of the pertinent telecommunications regulations worldwide. TRW will also manage the international testing of the Recover system. The portable verifier is the key to the installation and maintenance of the Recover system. Installation procedures for Recover begin at the resident verifier with trip planning. First, the IAEA inspector lists the facilities to be visited. Then, through an interconnecting cable, the resident verifier loads the portable verifier with all the information it will need to communicate with the listed facilities. The local installation procedure begins at the facility's on-site multiplexer. In this demonstration, we'll follow the installation and initialization of an electronic fiber optic seal. After the power and signal cables are connected, pressing any key activates communications between the verifier and the multiplexer. The user has a password which activates the unit and presents a display of the portable verifier status. The man-machine interface features of the portable verifier were carefully designed to permit confident operation by user personnel without extensive training. The displays prompt the user through the initialization procedures in a logical and understandable sequence. The key panel gives complete access to all system information necessary for initialization and installation of the monitoring units. Next, the fiber optic seals monitor is attached to the verifier and automatically initialized. The fiber optic seal can now be mated with the adapter containing the monitor. In this simulation, the seal is not attached to a containment. A communication link between the seal and the multiplexer, in this case a hardwired cable, is connected and the installation is complete. The portable verifier can also be used to review the status of all recover monitored sensors at the facility. This local use of the system may be especially helpful in checking the performance of sensors installed in sensitive or high radiation areas, or in cases where automatic telephone connection to Vienna is not established. In Vienna, at the Recover Command Center, the resident verification unit automatically goes about its routine business of interrogating multiplexers throughout the Recover system, looking for abnormal indications. When an alert is displayed, the system user logs in by entering his ID and password. In order to more closely examine the cause of the reported alert, a display alert function is selected. When the abnormal condition is identified to an authorized Recover system user, the flashing alert is terminated, indicating that the system has provided notice of the detected alert. Although the alert display is erased, the disk record of all system events retains permanently the occurrence of the alert. This data indicates that a camera unit in a film surveillance system at Whiteshell is inoperative. This data is simulated for the purposes of our demonstration. With this information, the system user can decide on a course of action and enter that action into the system memory. The user makes a note to inform the technical support staff that this surveillance system should receive attention. That note also becomes a permanent part of the Recover system record. The RVU user can also review the status of old alerts and monitor the progress toward their resolution. As alerts are resolved, old information is cleared and normal Recover system operations continue. Verifier functions also include the capability to review multiplexer status. Information on each facility in the system, including multiplexers and all monitors, can be displayed. The user also has available a display giving a summary of the Recover system status. Abnormalities are highlighted by special color indicators. Meanwhile, any new alerting conditions are constantly displayed as they occur, including any additional complications in existing alerts.
The ability of the Recover system to remotely diagnose the performance of IAEA safeguards equipment will be the most immediate benefit derived from use of the Recover system. The second benefit will be the remote monitoring of tamper indicators. This will assure the continuing integrity of deployed surveillance devices. The third benefit, which will be obtained after the Recover system is fully proven, is timely status information derived from the output of IAEA safeguards devices. Providing this information in near real time will assist IAEA in allocating and scheduling inspector resources.
To assist the IAEA in testing and evaluating the recover system, a technical coordinating group, including representatives from several member states, participated in discussions of the recover system design and assisted in the development of an international test and evaluation program. During 1980, installation of the recover system was made on an experimental basis in nuclear facilities in 8 cooperating countries. The resident Verifier unit was installed in IAEA headquarters. Beginning on 3 January 1980, the recover system began continuous monitoring of these experimental installations. Throughout the year, additional facilities and safeguards devices will be attached to the system. Through a rigorous testing program, data on the recover system's performance will be collected and evaluated.
Over several months, the system will be operated in a test mode, and data will be gathered on the system's performance. It is our hope that the performance, effectiveness, utility, and reliability of the recover system will justify its incorporation into IAEA use as a technique to enhance the effectiveness of international nuclear safeguards.